First of all, we're given that the mass of block M is equal to 8.4 kilograms, and its initial speed is, this is U equal to 4.2 meters per second. And we have the mass of the second block that is equal to capital M, and its initial speed is 0 since it is at rest. We are given the recoil speed, which is considered velocity of first block after collision. That is equal to the negative 0.4 meters per second. And we have given the time of the contact, which is t, equal to 0.2 seconds. Now we know the impulse of the first block is j, which is equal to change in momentum. So we can say that j is equal to the change in momentum, which is equal to final velocity minus initial velocity. So we can say that this is 8.4 into this is 4.2 minus 2 minus 0.4, and this comes out to be 38.64 kilograms per meters per second. Now we know the average force is given by impulse upon a time interval t. So we can say that F is equal to J divided by T. Now we put that into the equation, and the answer we get is 193.2 newtons. In this problem, an 8-gram bullet is shot into a block, which is resting on a frictionless surface, and the bullet remains lodged into the block, and it moves into an ideal massless spring, and the spring is compressed by 8.7 centimeters. The spring constant is also given, and we have to find out the velocity of the block plus bullet immediately before striking the spring. So here the kinetic energy of the block plus bullet system immediately before striking the spring converts into potential energy of the spring at maximum compression of the spring, where the system has zero speed. So the initial kinetic energy just before striking the spring is equal to potential energy of discipline at maximum compression, of the spring at maximum compression. Now initial kinetic energy will be equal to half m plus small m. V squared, capital M, is mass of the block, and small m is mass of the bullet. And V is the velocity just before striking the spring, and the potential energy of spring is half k, x squared. Here, x is the maximum compression of 8.7 centimeters, where the system has zero speed, so half cancels out, and now we can put the values. Mass of the block is 4 kilograms, mass of the bullet is 8 grams, which is 8 over 1,000 kilograms. V is unknown, K is the spring constant, 2400 newtons per meter, and X is the compression, 8.7 centimeters, which is 8.7 m squared. From this, we get V equal to 2.13 meters per second. This is the velocity just before striking the spring. Now we have to find the initial velocity of the bullet before it hits the block. So we can use the momentum conservation principle. Further bullet plus block system, initial momentum before striking the bullet is Pi, and it will be equal to the momentum after striking the bullet and before striking the spring. Now initial momentum is only due to the bullet because the block is at rest. So this is mass m of bullet times the velocity of the bullet and after it gets lodged into the block. The combined momentum is large M plus small m times V. V is the speed, which we found in the first part. See the speed of the spring of the bullet plus the block system gains after the bullet strikes the block, and this we found in the first part. So the mass of the bullet is 8 grams, 8 over 1,000 kilograms, times the mass of the block, which is 4 kilograms, and the velocity, 2.13 meters per second. So from this, we get V naught equal to 1066.6 meters per second. Alright, so here we have the circle that is going to be rotating with an angular acceleration of 0.01 radians per second squared. And so first we have to figure out how fast it's going to be going when it crosses the y-axis. So we're going to use our rotational kinematics. So when it reaches this point, it has traversed pi over 2 radians. And so we can use this time-independent kinematic equation to find the final angular velocity at that point. So omega squared, that's the final omega squared, is going to equal the initial velocity, which will be 0 squared plus 2 times the angular acceleration times t, times this change in displacement in the angular displacement. So if we solve this for omega by crossing this out, because it's 0, and then taking the square root of both sides, we get an angular speed of 0.0314 radians per second at that point. So now we need to figure out the time when it returns to its original position. So the first time that it makes one complete revolution. So for this, our new angular displacement is a full 2 pi radians. So we can use the displacement equation theta equals omega naught times t plus 1/2 alpha t squared, where this is the term is going to drop to 0 because our initial speed was 0. And we can solve this for time by solving it for time squared multiplied by 2 divided by alpha, and then take the square root of both sides. Plug in 2 pi for theta and 0.1 for alpha, and we get a time of 35.4 seconds. Okay, so for this question, let's look at force F1. This force makes an angle 30 degrees with the horizontal line, and therefore we have to find its shoulder with respect to the point O. Let's prolong this force F, and now let's draw the perpendicular line from O. Now we have to find the angle which will help us. So the angle which is labeled here is 30 degrees, and therefore torque created by the force F1 is AO times F1 times cosine of 30 degrees. And the torque breeds into one other rotation, which is clockwise. Now let's look at force F2. Force F2 is in the opposite rotation. The direction is counterclockwise, and so that is OB times F2. Meanwhile, force F3 is applied right at point O. Therefore, torque of this force is 0 Newton meters. So total torque then is torque created by F1 minus torque created by F2. So let's calculate it. That's 4.2 Newton meters, which is roughly 4.3 Newton meters.